Hello there. In this video, we're going to go through another topic related to the QPython package, which is to simulate when a queuing node has some finite capacity. What that means is that the waiting area or queuing area can only have some maximum number of, let's say, customers or patients or whatever at it at a time waiting. So that leads to a couple of cases that queue handles in different ways. And so let's just jump into reading the documentation since there's a bunch of conceptual stuff here. So a maximum queuing capacity can be set for each node. That's useful because maybe different services have different capacities, sometimes literally different amounts of physical space for customers to be waiting, or sometimes because of policies or other kinds of rules. Fair enough. This means that once the number of people waiting at that node reach the capacity, then that node cannot receive any more customers until individuals leave the node. This affects newly arriving customers and customers transitioning from another node differently. So newly arriving customers who wish to enter the node once capacity is reached are rejected. They instead leave the system entirely and immediately and have a data record written that records this rejection. On the other hand, customers wishing to transition from one node after finishing service at another are blocked. And this means that they remain at their original node in that blocked state, with a server which is unable to bring or begin another customer service, and hence it can have these knock-on effects at other parts of the system until space becomes available. Okay, so in order to implement this, we use the QCapacities keyword when creating the network. So let's just step through this code. Let's see, so at the very top, of course, we've got, I'm not sure, caps lock, my goodness. Okay, so we first of all import Q, as is so often the case with using any library, is you need to actually import it. Okay, so we import it, but then we need to define our network, and in this case we've got two nodes. So this is truly a network in a less trivial sense, that there's actually two different main places or service centers to be at. And they both in this case have exponential arrival rates with a rate of 2 and a rate of 1. And then we've got a corresponding set of service distributions that are both exponentials of rate of 1. This routing matrix means that if you're starting off at the first node, then you have a 0% probability of staying there and a 50% chance of going to the next node. And then there's a corresponding 50% not stated here of leaving the system entirely. And then if you're at the second node and you finish your service, there's a 100% chance that you just leave the system. Okay. Now we've got some number of servers at each node. The first one has 3 and the second one has 2. No problem there. That should all be fairly familiar. But this part is new, the queuing capacities parameter. So at the first one, at the first node, there is infinite capacity. You can have as many new customers entering the system as whatever happens to be simulated. But for the second node, it can only accept and have a total of 10 waiting at any given time. So there's two types of arrivals at that second node, right? There are the arrivals from outside of the system at a rate of 1. But then we also have, because of routing, arrivals from that first node as well. So when we're already at 10, what the documentation is telling us is that one of two things will happen depending on where the new customer is coming from. If the new customer is coming from completely outside of the system, they'll be blocked and actually rejected, sorry, is the right term, and they will not enter the system at all and will not return later, at least as far as the simulation tooling is concerned. So then there's being blocked. If you're coming from another node, if you're coming from node 1 to node 2, you may just end up waiting for a time at node 1 until the waiting area frees up a space in node 2. So for the simulation, it's not really any different to set up this simulation as any other. You should probably set a seed. You can set, define your simulation instance, and then simulate until maximum time. So let me see. We should be able to go finite capacity model, and there are no issues there. We'll look at some records in a moment, but we'll keep reading for the moment. Okay. So in the example above, the second node has 2 servers and a queuing capacity of 10. And so once there are 12 customers present, it will not accept any more customers. Yes, right. So that's a really great point. It's going to be a total of 12 at that service. why at that node. And the reason why is that even though the queuing capacity explicitly is 10, that's 10 for the waiting area, which also means that at that moment there can be at most however many servers worth customers, which is 2. So 12 in total. Great point that I missed there. So in the first node, there is infinite queuing capacity, and so no blocking or rejection will occur. If the queue capacities keyword is omitted, then infinite capacities are assumed. That is an uncapacitated system. And that's by and large in our video series, what we've been assuming up until now is that they have unlimited capacity to have customers arrive. Great. So rejection records. Any customer that is rejected and leaves the system will be recorded by producing a data record of the rejection. This will look like the following. Now yes, the docs are right in front of us, but I'd still like to reproduce this if I can. So get all records, and then we'll grab this record for a rejection records, and we'll print that record. Okay, so let's see. They're saying these records will have field record type as string rejection. As the string rejection, will have information about the customer, such as their ID and their customer class, which we can see here. Although I'm not sure that I see rejection. I actually think that this is different. That's interesting. So this could be an issue of when the example was made in the documentation, because I don't think I've coded this example any differently than how they have. Could be some details about how the pseudo-random number generation is different, because the record type I'm seeing here is actually record type service. But I wonder if maybe instead we can do a list comprehension and instead go record for record in records if record. Oh, you know what? No. We're fine here, because actually I forgot about one of the other things that they coded here, which is you can apply these filters to the get all records. Sorry about that. Let's pull this up again. So we got records dr0, and we'll print that expression. There we go. Now we have a record type, and what do you know? It's got exactly the same numbers now. Perfect. Okay, that's correct. So where were we with the paragraph there? They will have equal arrival and exit date representing the date they arrived and got rejected. Okay. And they will have a queue size at arrival showing the number of people at the queue when they got rejected. All other fields have not a number values. Fair enough. Okay, let's talk about blocking mechanism. So in queue, it does type 1 blocking. Or blocking after service, and it's implemented for what's called restricted networks. After service, a customer's next destination is sampled from the transition matrix. If there is a space at the destination node, that customer will join the queue there. This is just explaining what happens when they're coming from another node, which we already covered at a high level. We're just getting slightly more detailed here. So, else if the destination's node queuing capacity is full, then that customer will be blocked. That customer remains at that node with its server until space becomes available at the destination. That is, it stays at the node that it just finished service at. This means the server that was serving that customer remains attached to that customer, being unable to serve anyone else until that customer is unblocked. Okay. At the time of blockage, information about this customer is added to the destination node's blocked queue, a virtual queue containing information about the customers blocked to that node and in the order in which they became blocked. Therefore, when space becomes available, the customer to be unblocked will be the customer who was blocked first. That is, the sequence of unblockages happen in the order which customers were blocked. So that's something that maybe could be generalized in queue in the future, is to go, maybe in some cases you actually want to unblock according to almost like a service discipline type of thing, of some network scheduling kind of rule, but I think that FIFO is a good way to start. So circular blockages can lead to deadlock, and we'll talk about deadlock later in the documentation. There's actually a built-in mechanism for Q to detect that deadlock is happening. Now, information about blockages are visible in the service data records. That's fine, and we already kind of looked at that even for services. We saw an example earlier, I think. But just in case, let's run their example. And here, this is probably a cherry-picked example, 381, finite capacity. So there's a record service, and you can see that the amount of time blocked for this customer was 0.75 units of time. So in the case above, the customer ended service at time 87.31407, but didn't exit until the date 88.06478, giving a time blocked of 0.75070, etc. Okay, that is the basics of doing queuing capacities. From a programming perspective, all you need to do is specify the queue capacities as either a float inf if you need to be explicit, and then for the others where you're going to pick a finite number is to put in a strictly positive integer. Okay, with that, I will catch you in the next video. Have a good one.